So the next important point is close packed structure. Here each constituent particle is considered as a hard identical sphere here. So in case of one dimensional close packing, these spheres or the constituent particles, they are arranged in only one direction. They are arranged in row here, so that each sphere it is in touch with other. In this one they are arranged in one direction. Here you can see each sphere it is in touch with two other spheres. So its coordination number is taken as what? 2 here. The coordination number is the number of spheres that are in touch with particular sphere here. So each sphere it is in touch with two other spheres. That's why in one dimensional close packing the coordination number is 2 here. So they are arranged only in the one direction. You can take X here. Next comes two dimensional close packing, in which the constituent particles they are arranged in the X as well as in the Y direction. So it is having 2 dimension here. In this one again you will get two types of close packing, that is a square close packing and another is hexagonal close packing here. So here first one will go for square close packing, which is done by arranging one dimensional rows one above the other. Here these are the one dimensional rows which are arranged one above the other here, so that it is getting X direction as well as Y direction here. So it is a 2 dimensional close packed structure. In this one the second row is placed over the first row such that the spheres of second row are exactly above the spheres of first row here, like this. Again the third row is placed over the second row. Again the spheres are exactly one above the other. Here all the spheres are aligned horizontally as well as vertically here. In this one each sphere it is in touch with 4 other spheres. So for example, if I take this sphere, it is in touch with 4 other spheres. If you join the center of the remaining 4 spheres, you will get a square here. That's why it is called as what? Square close packing, in which it is in touch with 4 spheres. So 2 dimensional square close packing coordination number is what? 4. It is in touch with 4 spheres here. So what is the pattern obtained here? Pattern will be A type of pattern, because the arrangement of spheres in each row is same. This also A row, A, like that A type of the pattern will be continued here. And the space that is left between the close packed structures, that vacant space is called as what? Void or empty space here. The same thing will happen in case of hexagonal close packed layer, but the rule is different one. First row is placed A, the second row is placed over the first row, second row is placed over the first row, such that the spheres of second row they will fit into the depressions of spheres of first row. For example, these are the spheres which are in the first row, and the second row sphere it will fit into the depressions of sphere of first row, like this. This is the depression we call it as. So like this it is. So the arrangement of spheres in these two rows is different. I will call it as A and this will be B here. Whenever the third row is placed again, what happens here? Again the spheres of third row they are in alignment with the spheres of first row. Third row spheres and first row spheres, they are exactly one above the other here. So AB type of the pattern will be continued here, and here the coordination number will be this sphere. If I consider this is in touch with 6 spheres, so if I join the center of the remaining 6 spheres which are in contact with this sphere, you will get a hexagon. That's why it is called as what? Hexagonal close packed layer. Here the rows are placed one above the other in the staggered manner, so that the spheres of second row they will fit into the depressions of first row here. So 2 dimensional hexagonal close packed layer, the coordination number is 6 because it is in touch with 6 other spheres here. Pattern will be AB type of the pattern. And here 2 types of the voids are formed, that is a triangular voids, and this is a triangular void having its apex in the upward direction, and this is triangular void having its apex in the downward direction. Here triangular voids are formed, and here that square type of voids are formed here. If we compare these two close packing, here less space is vacant here, and here more space is vacant between the spheres. That's why the effective close packing is done in case of what? Hexagonal close packed layer. That's why here what happens? Square close packing efficiency is less than that of what? Hexagonal close packing in case of 2 dimension. So next we will go for 3 dimensional close packing. So the next type of important close packing is a 3D close packing. Till now we have discussed only 2D close packing, that is X direction and Y direction. Here we are getting what? X, Y as well as Z direction, so that it is a 3 dimensional structure. Z direction will be like this it is. okay, away from the board. Now 3D close packing from a 2D square close packed layer. Three-dimensional structures are prepared by placing the layers one above the other. Here I am taking two-dimensional square close packed layer is taken. This square close packed layer is placed one above the other, then you will get this simple cube. But the rule is the layers are placed one above the other such that all the spheres are exactly one above the other. They are aligned in the horizontal as well as in the vertical manner exactly. So that then you will get a simple cube. So its unit cell is simple cubic unit cell. And in this one, the three-dimensional coordination number, so that each particle it is in touch with 6 other particle. Along each axis it is in touch with 2 particle. Along x-axis 2 particle, along y-axis 2 particle, along z-axis 2 particle. So that the coordination number of each particle is what here? 6. Along each axis 2 particles are in touch. Hence 3 into 2 is what? 6 here. 3D coordination number in case of simple cubic unit cell is, that is 6 here. Next one. So the next type of important close packing is 3D close packing from two-dimensional hexagonal close packed layer. 3D structures are prepared by placing the layers one above the other, and here we are taking hexagonal close packed layer. Hexagonal close packed layers are placed one above the other. First thing you keep in mind, this hexagonal close packed layer, it is having two types of triangular void. One is having apex in the upward direction and another having apex in the downward direction. Whenever the second layer is placed over the first layer, what happens here? There are two possibilities. The triangular voids of the first layer are covered by the spheres of the second layer whenever second layer is placed over it. So these are the spheres of first layer and these are the spheres of second layer. So this second layer sphere is covering the triangular void of the first layer. Then there is a formation of what? Tetrahedral void here. Another possibility is the triangular voids of the first layer and the triangular voids of the second layer. They are exactly one above the other, and one is having its apex in the upward direction and another having its apex in the downward direction. They will not coincide. Okay, they are exactly one above the other, but their apex are in the upward and downward direction here. Then what happens? Whatever the space is left between these 6 spheres, these are the black spheres are in the first layer and red spheres are in the second layer. Then the void formed between them is what? Octahedral void. So first thing you keep in mind, whenever the second layer is placed over the first layer, there is a formation of two types of void. One is a tetrahedral void is formed and another is octahedral voids are formed. Now we will place third layer. For placing the third layer, again there are two possibilities. You can place the third layer such that all the tetrahedral voids that are formed in the second layer will be covered. Or another possibility is all the octahedral voids of the second layer are covered by the third layer. So there are two possibilities: covering all the tetrahedral voids of second layer or covering all the octahedral voids of the second layer here. Suppose the third layer is placed such that the spheres of third layer, they will cover all the tetrahedral voids formed in the second layer. Then what happens? Suppose it is the first layer, second layer is placed, means what happens here? Octahedral and tetrahedral voids are formed here. Now we are placing the third layer such that all the tetrahedral voids of second layer are covered. Then what happens? This type of pattern is obtained. A, B type of pattern is obtained because the arrangement of spheres in the first layer is this one. In the second layer it is like this, so that these two are different, means I will give it as A and this is B. Again, whenever you place third layer, the spheres of third layer, they are exactly in alignment with the spheres of first layer, so that AB type of the pattern is obtained here. Then the crystal lattice obtained is called as what? Hexagonal close packed layer. Three-dimensional hexagonal close packed layer is obtained here. Then the three-dimensional coordination number is what? 12 here, because in the each layer that particle it is in touch with 6 other spheres here. This is like this, it is in touch with 6 spheres, and above 3 spheres are there and below 3 spheres are there. Total one particle it is in touch with 12 particles, so that the 3D coordination number in case of hexagonal close packed layer is 12 here. Always you keep in mind, if you place the third layer such that it covers all the tetrahedral voids of second layer, then the close packing obtained is hexagonal close packed layer. 3D coordination number is 12 here. Next, covering octahedral void. Then ABC type of the pattern is obtained. ABC, see here. In this one, the arrangement of spheres is different in this one and this one. A, this is B, and this is C here, because all the three layers, the arrangement of spheres is different, so that they are given as A, B, C. Whenever fourth layer is placed, the spheres of fourth layer, they are in alignment with first layer, so that they are same here. Again it is given as A. Again fifth layer is B. Again sixth one is what? C. Like that ABC type of the pattern is obtained. So the crystal lattice obtained is FCC or cubical close packing is obtained here. Then again the three-dimensional coordination number is 12 only. In each layer, that particle is in touch with 6 other spheres, and above 3 spheres and below 3 spheres. The total coordination number is 12 here. So this is very important, you have to remember for the entrance point of view. This is the octahedral void. It is a combination of two triangular voids surrounded by 6 spheres, and this is a tetrahedral void. It is a combination of 4 spheres. 3 spheres are in the one layer, and the second sphere is placed above the 3 spheres here, so that there is a formation of tetrahedral void. Covering tetrahedral void, AB type, SCP. Covering octahedral void, ABC type, and FCC or CCP is obtained. 3D coordination number is 12 here. Next point. So the next point is position of these voids. We know that during the close packing of spheres, there are two types of voids are formed. One is a tetrahedral void is formed, and another is octahedral voids are formed. Now the position of these voids. Now for simplicity, we know that for FCC, Z is equal to 4 means for FCC the number of particle per unit cell is equal to 4. So that the number of close packed spheres will be equal to what? 4 here. Now the position of octahedral void. Octahedral void is present at the body center and at the edge center. So already we know that the body center contribution is 1. How many edges are there? 12 edges are there. So the contribution of each edge center particle is what here? 1 by 4. That's why 1 plus 3 is equal to 4. Total 4 octahedral voids are present here. So the position of octahedral void is very important. One octahedral void is present at the body center, and they are present at the center of the each edge here. So edge center and body center, this is the position of octahedral void here. So there are 12 edges are there, 1 by 4. That is the contribution of edge center particle is 1 by 4, so that it becomes as 1 plus 3 is equal to 4 here. Next, tetrahedral void. On each body diagonal, 2 tetrahedral voids are present. Already I told you the number of body diagonals present in the cube. Total 4 body diagonals are present in the cube. 8 corners, 4 body diagonals are present. On each body diagonal, 2 tetrahedral voids are there. So that 4 body diagonals are there means total 8 tetrahedral voids will be obtained. Now from this conclusion, see here, 4 particles are present in the FCC, 4 number of octahedral voids are present, and 8 number of tetrahedral voids are formed here. From this one, the number of close packed spheres is equal to n. Suppose n number of spheres are involved in the close packing, then n number of octahedral voids are formed. The number of octahedral voids formed will be equal to n, and then the number of tetrahedral voids formed will be equal to what? 2n. For example, 10 spheres are involved in the close packing, 10 octahedral voids are formed, and 2n number of tetrahedral voids are formed means 20 tetrahedral voids are formed here. So for FCC, the number of close packed spheres is equal to what? Z is equal to 4. So that in FCC 4 octahedral voids are there and 8 tetrahedral voids are there. Next point is, in the ionic solids, cations and anions are involved in the close packing. So since they are having a large difference in their size, both cannot be involved in the close packing. That's why these larger anions are involved in the close packing, and these cations, they will occupy what? Voids here. See here, these larger anions, they are forming close packing, and the space left between them in those voids, the cations are occupied here. And it is not necessary that all the tetrahedral and octahedral voids that are formed, they must be occupied. Only the fraction of octahedral and tetrahedral voids are occupied. If the cation is larger one, it will occupy octahedral void. If the cation is a smaller one, then it will occupy what? Tetrahedral voids here. You have to remember this formula. It is very important for entrance point of view, because here it is used to calculate the formula of the compound. So the formula of the compound is calculated based on this formula only. So that is what? Formula of the compound. Number of close packed sphere is equal to n. Octahedral voids formed are n. Tetrahedral voids are formed are 2n here. What are the total number of voids here? The total number of voids will be equal to n plus 2n. This will be 3n. The total number of voids will be equal to 3n here. So the next point. So the next important point is packing efficiency. Packing efficiency is equal to volume occupied by the spheres that are present in the unit cell. And for example, here for simple cube you have to take number of sphere is equal to 1, for BCC you have to take number of sphere is equal to 2, for FCC you have to take number of sphere is equal to 4 here, so that the volume occupied by 1 sphere, volume occupied by 2 sphere, volume occupied by 4 sphere, like that you have to take, divided by total volume of the unit cell. That is total volume of the unit cell is nothing but what here, A cube. A is the edge length, means if you take the cube then you will get total volume of unit cell. So the packing efficiency is equal to volume occupied by the spheres divided by total volume of the unit cell into 100%, okay, into 100 it is. Then in a cube, one face diagonal value is equal to root 2a, okay, one body diagonal value is equal to root 3a, okay, and this root 2a will be is equal to 4r, 4 times of the radius. Here also it is also equal to 4 times of radius. Now for different cases, in case of FCC closed packing is similar to that of HCP and CCP also, okay. In FCC the spheres are in touch along with the face diagonal, so that one face diagonal value is equal to root 2a, its value is equal to what, 4r here. Then for FCC z value is equal to 4. These formulas are very important for entrance point of view, so that they will ask problems on these formulas only. Z is equal to 4 for FCC, A is equal to edge length value is equal to what you can write here, 2 root 2 r. Next R value is equal to, just you rearrange this one, A by 2 root 2. Next packing efficiency in case of FCC is 74%, and the empty space left, that way I can write it as void, okay. The percentage of void is equal to 26%. So 74% of space is filled by the spheres and 26% is left vacant here. Similarly, in case of FCC, for FCC the distance between the two nearest neighbors is equal to, that will be is equal to face diagonal divided by 2. Face diagonal value is what, root 2a divided by 2. This is nothing but a by root 2. Directly you can take a into what it is, 0.707, you can take like this, okay. Next for BCC, body diagonal value you have to take, because in case of BCC 4 spheres they are in touch along the body diagonal, okay. Then in case of body diagonal, root 3a is equal to 4r, because the radius of 4 spheres, that will be is equal to 4r, you have to take here. Then z value is 2, a is equal to 4r by root 3, r is equal to root 3a by 4. Then packing efficiency in case of BCC is 68%, and the percentage of void is 32. Total space filled is 68%, empty space left is what, 32%. For BCC the distance between two nearest neighbors is body diagonal divided by 2. Body diagonal is what, root 3a divided by 2, that will be is equal to a into 0.868. Directly you can multiply these values. Next point, in case of simple cube, that spheres are in touch, that corner spheres, they are in touch with each other. That's why here one edge length a is equal to 2r, this is also r and this also r here, so that a value is equal to what, 2r here. Then z value is 1 for simple cube, a is equal to 2r, r is equal to a by 2, rearrange this one. Then packing efficiency in case of simple cube is 52.4, and the percentage of void is 47.6 here, okay. So the packing efficiency is maximum in case of HCP, CCP or FCC you can take, because it is 74, and then comes BCC 68%, then is simple cube, that is 52.4%. These are the very important formulas for the entrance point of view. You have to remember all these formula. Based on this only we are going to solve the problems. Next, so the next important point is density of the unit cell. This one, density is equal to mass by volume. If edge length is a, then volume of the unit cell become as a cube. Then mass of the unit cell. Mass of the unit cell is number of particle per unit cell, that is z value, into mass of the each atom. So density is equal to mass by volume. Mass is what, number of particle per unit cell, z value, and mass of the each atom, divided by volume of the unit cell, that is a cube. Here mass of the each atom, small m, is nothing but what, molar mass divided by Avogadro's number here. So this small m is replaced by what, molar mass divided by Avogadro's number. So the formula become as density is equal to z value into molar mass divided by Avogadro's number into a cube here. Here this small m is nothing but, here molecular weight, it is the mass of the Avogadro's number of particles. So the mass of the one particle, is what, here small m is equal to molecular weight divided by Avogadro's number here. So in this one you have to take care about the units also. if the molar mass is written in the grams and the edge length is given in the centimeter, then density will be in the gram per cubic centimeter. Suppose molar mass is given in terms of kg, then edge length is in terms of meter, then density is what? Kg per cubic meter here. Then here how to select this Z value? Z value is for FCC, CCP and HCP. They will give in the problem. It will crystallize in FCC, CCP or HCP like that. Then you have to take Z value is equal to 4 here. Then for BCC, Z is equal to 2. For simple cube, Z is equal to 1. So by using this data, you can calculate any one of these parameters. They will ask density giving remaining things, or else they will ask you to calculate the molar mass. They will give density here. Okay. So like this, you have to calculate the density of unit cell.